Yes, my screen is visible to all.
Yes, sir.
Yes, sir.
So if we are going with the fraction part, like for example, if I have a any binary number, okay, like 1101, in that way, how we convert into the decimal form? Sorry, decimal form. We multiply with the weighted base 2, okay, because it is a binary number. If I want to convert into the decimal, so what should I do? I just multiply with weighted. 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, and 2 raised to power 3, and so on. Okay, so we can convert into the decimal. Now, if any number will be given is 1101.110, like that way. So here we start with the 2 raised to power 0. If we go with the beyond that particularly point, or basically toward the right side of the decimal, so we multiply with the 2 raised to power minus 1. Okay, so 1 into 2 plus 1 into 2 plus 0 into 2 plus 1 into 2 dot 1 into 2 plus 1 into 2 plus 0 into 2. Okay, now we provide the power. So that is a 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3. Here, if we go to the right side of the decimal point, so 2 raised to power minus 1, 2 raised to power minus 2, and 2 raised to power minus 3. Okay, so
Yes.
the number is 8 plus 4 plus 0 plus 1 point, that is 2 raised to power minus 1, that is 1 by 2 plus, that is 1 raised to power 1 by 4. Okay, 8, 4, 12, and 113 point. 1 by 2 is 0.5, and 1 by 4 is 0.25. So 0.5 plus 0.25, that is a 0.7. This is for
Sir,
binary to
now,
decimal.
sir, now if we convert the fraction part into octal or hexa,
Yeah.
so what we do? We have to
Okay.
multiply fraction whole fraction part by 8.
Wait a minute. That is the conversion from binary to decimal. Now, if we convert from decimal to binary, like I'm just taking the same number, 13.75. Okay, we know the 13. How we solve 13? Divide by 2. Okay, and which one is a reminder? We can put it in the left side. So if I divide 13 divided by 2, so we are getting a 6, and 1 is a reminder. If we again divide by 2, so that we are getting a 3, remainder is 0. Again divide by 2, 1, and remainder is 1. Okay, now the remaining number 1 is less than 2, so we can't divide 1 with 2. So the representation is from bottom to top. So 13 is 1101. Okay, now we go to the 0.75. So 0.75. What should I do? I have to convert it to the binary, so I multiply with 2. Okay, if I want to convert into the octal, multiply with 8. If I want to convert into the hexadecimal, multiply with 60. Okay, now 0.75. If 0.75 multiplied by 2 is 1.5, so we keep 1 as it is, and 0.5 is again multiplied with 2. So 0.5 multiplied by 2 is 1.01 as it is. Remainder is 0. If I multiply 0 with 2, so we are always getting the 0. So 1, 1. Here we are taking from top to bottom. Okay. If I multiply into the octal part, so 0.75 multiplied by 8. Okay, we are getting 6.0. Okay, now 0 is the decimal point, so 0 multiplied by 8, we always getting a 0. So the answer is 6. So that means this 0.75 in decimal, it will be equal to 0.11 into the binary, or that will be 0.6 into octal. Okay. Now if we want to convert into the hexadecimal, 0.75 multiplied by 60. So we are getting a 12. 12 is C. Okay. So point C in hexadecimal. Clear?
Yes, sir. Clear. Thank you.
12.0. This is the 12.0. 0 multiplied by 16, we always get it at 0. So only the C is part. Okay. Now if the number is, so this is the binary to, if decimal to binary, octal and hexadecimal, we convert in this way. Okay.
Yes, sir.
If the number is more than point, okay, so we divide by 8. Okay, if like 13, we want to convert 13 into the octal. So how we convert 13 into octal? Divide by 8. 1 and 5 is the remainder. So the number is 1 5. Okay. If you want to convert into the hexadecimal, divide by 16, the number 13 is less than 16. So we are getting 13 as a reminder. 13 is D. Okay, so 13 in decimal is equal to 1101 in binary, or that is 15 in octal, or that is D in hexadecimal. So binary to decimal, octal or hexadecimal, the method is same. Okay, binary divided by 2, octal divided by 8, hexadecimal divided by 16. If the number is decimal point, so multiply by 2 in binary, multiply by 8 in octal, and multiply by 16 in hexadecimal. Understood?
Yes, sir.
Now, either convert it from binary, octal, or hexadecimal to decimal. So what should do we do? In the binary, we multiply with the weighted sum. Okay, we multiply with 2 raised to power weight. So if number is given that 1101, we multiply with 1 into 2 plus 1 into 2 plus 0 into 2 plus 1 into 2. 0, 1, 2, 3. This is the binary to decimal. If number is 64, base 8. Okay. So what should we do? We multiply with the weighted. So 6 into 8 raised to power 1 plus 4 into 8 raised to power 0. So that is, if any number is given, is the AC base 16. So A into 16 plus C into 16 raised to power 0, 16 raised to power 1. So that is in decimal. Okay, so by decimal to binary octal hexadecimal method is same, and binary octal hexadecimal to decimal the method is same. Clear?
Yes, sir.
Now any doubt in the number system part? Just any doubt? No?
The
No, sir.
practice assignment question number 19.
Practice assignment question number 19, week 2.
Yes, sir. Like how we get -1.
Okay, okay, okay. Match. Practice assignment. Question number 19. The decimal value of n bit 2's complement binary number is this one.
Yes, sir.
Okay. So you are aware about the 2's complement?
Yes, sir.
So what is 2's complement first of all?
We have to add 1.
We have to add 1.
1. Yes, sir.
Okay.
In 1's
So
complement, we have to flip the digits like 1 into 0, 0 into 1, and then we have to add 1.
add 1. Okay, that's fine. So basically, if we are talking about the negative number, okay, so we are taking about the 1's complement, we can take about the 2's complement, or we can represent into the sign magnitude. Okay. If the number is positive, either we can take 1's, either we can take 2's, either we can take sign, no change. Okay, like for example 13, if I want to represent, the binary representation is 1101. Okay, and generally if we are talking about the ones, twos, complement and sign magnitude, the range will be changed. Okay, in the normal binary number with a 4-bit, we can represent our data with a 4-bit. We can represent our data from 0000 to 1111. That means 0 to 15. But for the ones complement, for the sign magnitude, or for the twos complement, the range will be changed from negative to positive. Okay, with a 4-bit, either the range from -8 to +7 or -7 to +7. Okay, so if we want to represent a 13, okay, so we have required a 5-bit, because after +7 we have to add one more bit. So for 13 we represent the 5 bit. So either we represent 13 because it is a positive number, so the binary representation, as well ones complement, as well twos complement, or as well sign magnitude, all are ones, twos and sign. Clear? Any doubt?
Sir, so one doubt here, like for we don't have to take the flip the bits for one
If the number
complement.
is positive,
If the number is positive, all the representations are the same in this
same.
case.
Yeah, because ones, twos or sign magnitude is only required to represent the negative.
Okay. Okay. Sir.
Okay, if the number is already positive, why we represent in the ones complement, twos complement, sign magnitude?
Okay, sir.
Okay. Now the thing is that if we represent into the ones complement, I just take one example is 1111. Okay, and I say that this is the ones complementary. Ones complement. So what is the basically decimal equivalent of this one? First of all, check MSB. MSB is 1. Okay, MSB is 1. That means the number is negative. Clear? Now after that, what we do, we flip all the bits. Because it is a ones complement, we flip all the bits 0, 0, 0, 0. So the -0 is the representation. of this one's complement representation in decimal. If I say the same number 1111 and I just say that it is a 2's complement, so first of all check the number. The number MSB is 1, that means the number is negative. Now we take the 2's complement. So how we take the 2's complement? Start from the right side. When first ones is come, after that every bit will be okay. First one is as it is, till first one as it is, after that every bit will be free. So that is representation of 1. So minus 1 the representation. Okay, again I repeat, till first one, start from the right side, till first one every bit is same, after one every bit will flip. Clear? Or you can take by one's complement, first of all take the one's complement 0 0 0 0, then add 1. So 1 0 0 0. Clear? Any doubt?
Yes, sir, clear.
1 1 1 1. If it is represented as a sign magnitude, the representation is first of all check MSB. MSB is 1, that means minus. Leave this one and the remaining, this is the decimal equivalent. Okay, so 111, the decimal equivalent is 7, so minus 7 based. This is the sign magnitude. Any doubt? Yes, no, any doubt?
No, sir.
Now,
No, sir.
in place of 4-bit, I just use the 5-bit 1 1 1 1 1. That is 1's complement, 1 1 1 1 1, 2's complement, and 1 1 1 1 1. That is a sign magnitude. What is the decimal equivalent of this one? Check first MSB.
Yeah,
You know about the MSB and
Negative.
LSB part?
negative.
Negative. Yes, sir.
MSB and LSB, no, no?
Yes, sir.
Yes, yes.
So 1 negative, flip all the bits. So 0 0 0 0 0. So minus 0. Any change? Either I should represent in the 4, either I should represent in the 5-bit. No change. The decimal equivalent is same. Similarly, for 2's complement, MSB negative. Okay, start from the right. First one will be as it is. After that, every bit will be. So that is minus 1. So minus 1 is 10. Okay, but sign magnitude, the number is changed. First one is the M negative 1 negative. Now the decimal equivalent of this one 1 1 1 1. Okay, decimal equivalent of this one. So this is the 15. Clear? Now if we take the n bits, all n are 1. Any change in the data? For the 1's
No,
complement,
sir.
no change. For the 2's complement, no change. For the sign magnitude, yes, definitely it will change. Okay.
Yes, sir. Got it.
Now you got question number 19.
Yes, sir. Got it.
Now in the week 3, any other doubt related to the week 2?
No doubt, sir.
Okay.
No, sir.
Sir, similar to this, we have a question in the graded assignment uh, for week 2. Now it's
Okay.
asking about the 2's complement of a 2's complement and 1's complement of a positive number of the same number. So
Wait a minute. Which question?
question number
14,
question number
14 and 15.
14 17 and 18, sir. Sorry,
Oh, sorry.
18 and 19. 18 and
Okay,
19.
okay. Now it changed. Okay. Now what?
Sir, here, like it's asking, it's a positive number. So, like you mentioned earlier, like the 2's complement and the 1's complement is going to remain the same, right? For these.
Mm-hmm.
So, like there's not going to be any difference in the number of.
That is your thinking. We will solve after the deadline is over.
Okay.
Okay.
Okay, sir.
Now, yes. Any other doubt related to a week two? Yes. Any other doubt? Week two.
No, sir.
So yeah, one more thing is that sometime in the if you go with the competitive exam like GATE and other, okay, so they ask one question like what is the range formula, range of two's complement. I think that will be covered. I just and sign magnitude. So if we are talking about the range, so for the n bit, the range of two's complement number is minus of 2 raised to power n minus 1 to plus of 2 raised to power n minus 1 minus 1. That means if we have a 4-bit data, okay, so according to the 2's complement, we can represent the range from minus 8 to plus 7. If you put n is equal to 4, so you can get the range minus 8 to plus 7. That means if any number will be in this range, okay, in 2's complement, we can represent that number with 4 bit. Clear?
Yes.
If we are talking about the 1's complement, the range is minus of 2 raised to power n minus 1 minus 1 to plus of 2 raised to power n minus 1 minus 1. That means again it 4-bit data, so the range is from minus 7 to plus 7. Can anyone tell me why? Yes.
In 1's complement, we have two representations of 0, minus 0, plus 0.
Yeah. In the 1's complement, we have a two different representation of plus 0 and minus 0. If we represent a 0 plus 0, so we are getting 0, 0, 0, 0. If we are getting a minus 0, so 0, 0, 0, 0, and again take the 1's complement, so all will be the 1, 1, 1. Two different representation. Okay, so that's why 7 and 7, 14, and 2 plus 0 and minus 0, 16 will be the total representation with 4 bits. Similarly, if we are talking about the sign magnitude, The range is again same, minus of 2 raised to power n minus 1 to 2 raised to power n minus 1 minus 1. Okay, that means for 4-bit, we can represent from -7 to +7. The reason is same. +0 will be 0, 0, 0, 0, and -0 will be because of 1 minus it is a 1 and binary decimal 0 is 0. Okay, the two different representation. Okay. So sometime in the question they are asked you the range. Sometimes they are asking the what is the minimum. Yeah, minimum is smallest number will be represented with the 4-bit data, 2's complement data. Okay, the answer is -8. The smallest number is -8, -7, and -7. Okay, remember that -1 is not a smallest number. Okay, you sometimes you mention the -1 because the option it is given the -1, so you just mark the -1 because minus sign and 1 is the smallest number. Okay, but -1 is not a smallest number, -8 is the smallest number. Okay, understood? Any doubt?
No, sir.
Generally this type of mistakes we always saw. So just remember with this, the smallest number is the -8, -7. Now, just one more thing is that sign extension is covered or not? Sign extension.
Sir, it is in B3.
Okay. So, yeah. Sign extension is what? Like, for example, we have a number 13 in the decimal. Okay. We should represent as a 1101. The 4-bit is required to represent that data. Okay. Now the thing is that, sorry. Now the thing is that if we use this 4-bit data for a system or like for a computer or basically any particularly processors, the processor I think they have 8-bit processor or 16-bit processor. Okay, so that means minimum 8 bits are required. Minimum 8 bits are required. You have only 4 bits. So what should you do? You have to change this 4-bit data into the 8-bit data. That is called the extension. Okay, that is called the bit extension. So you represent this 4-bit data into the 8-bit data 00001101. Now you convert this data into the hexadecimal code and you just use that hexadecimal code into the processor. Okay, or you can use the binary data also. So generally 0 A B C 13 D 0D 0D is your data. 0D weight 16. Okay, so that's why we require to extend our bits either that bits into the 8-bit or 16 bits. Okay, so this is called the bit extension. Bit extension. That bit extension is quite easy when we go with the binary number, because in the case of binary number, what should we do? We only add how much of zeros are remaining. We use that particularly to fill the zero. This is called the zero padding. Okay, this is called the zero padding. We insert zeros. How much zeros? That is dependent on how much bits we have and how much bits we require. So like we have a 4 bits and we require a 8-bit data. So what should we do? We add a 0 padding. 4-bit we use zeros, 4 zeros we use, but that zeros will be used in the MSB. If you insert into the LSB, that is the complicated. Why? Your weight will be changed. Bit weight will be changed. Here the bit weight will be the 2 raised to power 0. But now this will be the 2 raised to power 0, 1, 2, 3, 4. So you change your bit weight. Okay. So that's why always we extend our bit in the MSB part, because if you add MSB, like similar to it, you have 100 rupees, either you represent a 0100, that is again 100. If you represent a 00100, 100 rupees. Okay, or you have a 500 rupees, you add a 0000. How much zero you can add? You can add. That is always same 0, 500. Okay, but if you add in the lower side, so that is a 500. If you add a 10, that is a 5,000. If you add one more zero, that is a 50,000. So basically, you change the weight. That. Okay, so bit extension always do in the MSB part. For the binary, it is very simple. It is called the 0. Okay. Now, if we go with the 2's complement, we already discussed the 2's complement, like 1, 1, 1, 1. That is also -1. If we add a 1, 1, 1, 1, 1, that is also -1. Or we add a 1, 2, 3, 4, 5, 6, 7, 8, or 10, any value, that is also -1. Okay, so in the 2's complement, what we are calling is that the MSB padding. Okay, MSB padding. What is the meaning of MSB padding? The bit that is available in the MSB, we use this bit to extend our bit size. Okay, if we have a 4-bit, so we are using the 1, 1, 1, 1. If we require a 8-bit, so what should we do? We use this MSB, just copy and paste 4 different places, 1, 2, 3, and 4. The remaining data will be same. The number will be same. The representation will be same. Okay, so it is called the MSB padding. So we only copy and paste the MSB part. Okay, why should I say the MSB part? Like for example, here it is a negative number. For example, the number is positive. That is 2's complement form. Now what should we do?
0, 0, 0.
We add a 4 zeros. We add a 4 zeros. So which particularly bit is the MSB bit? We just copy that MSB bit and paste it the places how much bit we require. Okay, so that's why we call the MSB padding. We are not saying this is the 1 padding or 0 padding, because that is for positive it will be the 0, for the negative it will be the 1. So that's why we call the MSB padding. Understood?
Yes, sir.
Yes, sir.
Now,
Yes.
1's complement. In the 1's complement, we already see that 1, 1, 1, 1 base 1's complement is always -1 base 10. If we are using the 5 bits in the 1's complement, that is also -1 base 10. Okay, we already see here this one. Okay, so again, the 1's complement, it is also called the MSB padding. Why MSB padding? If the number is negative, we add 1 in the MSB part. If it is a positive number given in the 1's complement, we add 0 in the that. Okay, so again it is called the MSB padding. So if we require, if the data is given this one, I have to convert into the 16-bit. So what should I do? Add 12 MSB. 4 is the data, 111. So that is your 16-bit data. That is also -1 based. Okay, the number is positive 0111 given in the ones complement. So that is, if I convert it to the 16-bit, 0000 0000 0000, then 0 ones. Okay, so this is called the bit extension for ones. Okay, so for the binary, we add the 0 padding. Normal binary number for the ones and twos, we use the MSB padding. Now the sign magnitude. Okay, number is given as a 111. That is the sign magnitude. What is the decimal equivalent? Check MSB. MSB is 1. Okay. Then the decimal equivalent of 111 is the 7. So that is the -7. Paste. Okay. If we add 0 here to increase the number of bits, so what should happen? If we add a 4 zeros to convert into the 4 into 8 bit. So now MSB is 0. So that is the number is positive. Decimal equivalent of remaining bits. This one. So 1, 2, 4, 8. So that is the 15. So the number is +15. Paste. Okay. So we can't add a 0 in the MSB. Now we check with the 1. So we add 1. Okay. We add a 4 ones. The 4 number is already here. So this one is minus. Okay. And the decimal equivalent of this one. So 1, 2, 4, 8, 16, 32, 64. So the number is all ones, that means 127, and because of this MSB, this is a negative, so -127 based. So that means we can't add a 0 or we can't add a 1 in the MSB part. So what should we do? We have to maintain a sign, so we can't change the MSB. Okay, so the number is given as a 1 1 1 1. So we can't change the MSB. So 1 is MSB. Now this 3-bit we have to convert into the 7-bit because 1 bit is already there. Okay, 3 to 7. So now this particularly number will be the decimal equivalent. So what should we do? That is simple to the binary. Okay, if we just neglect this one, so this is the binary number in sign magnitude. We convert this binary number into the decimal simply. Okay, so we apply the method to how we convert how we extend our bits in the binary. So we add a zeros. We add a zeros. Now we check the decimal equivalent. So because of MSB it is a minus, and because of this one the binary number is 7. So -7. Okay, so the binary number we use the 0 padding. For the ones or twos complement we are using the MSB padding, but for the sign magnitude the method is completely different. You can see we can't change the magnitude positive or negative, so we keep MSB as it is. We can't change the binary number except this one. Everything will be the binary. So we use the method how we extend our binary bits. So in place of 3, we want a 7 bits. So what should we do in the binary number? We use a 0 padding. So we use this 0 padding. So the number is 0. Okay. Any doubt?
No, sir. No, sir.
Okay. So if we solve some questions, mm, -7 base 10, you have to represent this as a 8-bit hexadecimal. Okay.
Sir, in
But
two element format or
you have to solve for 3. That's why I'm not mentioning.
okay, okay.
First of all, the number is negative, so binary representation is not possible for the negative. So binary method is different. Okay. Only 3 remaining method is 2's complement, 1's complement, and sign negative. Okay. So first of all, we represent 7. The representation of 7 is 0, 1, 1. Now the number is negative, so we have to take the 2's complement. How we take the 2's complement? Start from the right, where the first one will be coming. Till that, no change. After that, every bit will be flipped. Okay. Now this is the 4-bit data. We have to convert into the bit extension. So the number is 11111001. Okay. Now, how we convert into the hexadecimal? Just make a group. 4-bit starting from the right. So 4 and 4. So that is the 15. 15 represent is the F, and this is the 9. F9. If we are talking about the ones complement, so first will represent 7, then ones complement, bit extension, now make a group. This is the group 4, this is the group 4. Starting always, always from the right, not from the left. Okay, group will be from the right. So this is the F and 8. If you are talking about the sign magnitude, so the sign magnitude is the 1 and 1, 1, 1. Sorry, initially we declared as now sign magnitude we have the 1, 1, 1, 1. Now with the bit extension we require 0, 0, 0, 0, 1, 1, 1. Now make a group, this one and this. So that is 8, 7. Verify your answers.
Sir, here if we instead of -7 we have +7 and we are asked to do this, so then the 2's complement number will be just 0,
We
0,
don't
0.
we not require this step.
Okay, so it will be just 0, 0, 0, 1, 1, 1, 1, 1, 1,
Yeah,
1, 1. And one's complement will also be the same.
same,
Only the sign magnitude. Okay, the sign magnitude will also be the same, right?
also same.
Oh, okay.
Any doubt in this one? Yes or no?
No, sir.
No, sir. No, sir.
Now the question number -56 is 10. You have to represent a 16-bit hexadecimal 2's and 1's count. A long neck. Just anyone?
So for 2's complement, it's f f f 8
FFF?
8.
Okay. In 2's complement. And in 1's complement, the FFF7.
So I've got FFC7 and FFC8.
FFC8 in 2's and FFC7 in 1's. Any other answer? We have two different options. Okay, so first of all, we write it 56. This is the 56 in binary number. Okay, we want to convert into the 2's or 1's complement, so we required one extra bit. Okay, so this is the plus 56. Now take a 2's complement or 1's complement. So what is the method of 2's complement? Start from the right till first one, no changes. So 0, 0, 0, 1. After that, every bit will be flipped. 0, 0, 1. Okay, and in 1's complement, 1, 0, 0, 0, 1, 1. Okay, so this is the minus 56. Now we have a bit extension. So we have a 7 bits, we require a 9 more bits. 4, 5, 6, 7, 8, 9. Then the remaining data 1, 0, 0, 1, 0, 0. And 1, 1, 1, 1, 1, 1, 1, 1, 9 ones, and remaining data is 1, 0, 0, 0, 1, 1, 1. Now make a group, 1 group, 2 group, 3 and 4. So this is the 7, 1, 1, 0, 0. So 1, 1, 0 is 12. 12 is C. And all 4 ones, so that is the F. F. Okay. Similarly, this one. So F, F, C, and this is the 1, 0, 0, 0, that is I. Okay. Any doubt you can ask. No doubt. Can we take one more question? Or is it clear to all? Yes, students, any doubt? Can we take one more question?
Yes, sir.
Yes, sir.
We have a number -111 is 10 represent into the 16 bits, 8-bit hexadecimal. Okay, all three methods. One's complement, two's complement, and sign magnet. So 111, the binary number is okay. So binary number is for same for everyone. Okay. Now you see that number is 8-bit, already 8-bit. Okay, and we have to represent the 8 bits, so we do not require any bit extension here. Okay, we are not required any bit extension because already we have 8 bits. If the number of bits is less than 8 bit, then we require a bit extension. But here already we have a 8 bit. Now convert into the ones complement, two's complement, and sign magnitude. One zero zero one zero 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 zero. Okay. Now make a group. So group of 4 and group of 4. So that is a 90. Group of 4 and group of 4. That is 91. Group of 4 and group of 4. So now E F. Any doubt? You can convert into the octal also. 8-bit octal also. So the method is same, only the grouping is different. Okay, so in the octal, we have a group of 3. So 3, 3, one more required 3. So that is the 2, 2, 0. So 220 base 8. Group of 3, and 0, so group of 3. So 2, 2, 1 base of 8. Group of 3, group of 3, and 1 0 is added group of 3. So that is 3, 5, 7 base 8. Okay, any doubt?
No, sir.
So I think we will stop here. In the next class, we start with the logic gates.
Okay, sir.
Excuse me, sir.
Yeah,
Sir, we did not get the link of the live.
yeah, Pinky, I just update in 5 to 10 minutes. Okay,
Okay, sir.
that will be taken by the Bhavya ma'am, so they don't have the sheets. Okay, so I will update it in 5 to 10 minutes.
Okay, sir.
Any other doubts? Thank you all.
Thank you, sir.
See you.
Thank you, sir.
Okay, sir.